Today's presentation will focus on a multi-site performance review of projects using slow-release electron donor and bioaugmentation co-application strategy. This is a continuation of a webinar given last year, in which we reviewed strategies for remediation of chlorinated solvents in groundwater. Over the past year, we've been able to gather more comprehensive performance data from these sites, which has given us insight into when it is optimal to perform supplemental injections. So we're excited to share this information with you today. With that, I'd like to introduce our presenter for today. We are pleased to have with us Mr. Steven Sittler, Senior Project Manager at Patriot Engineering and Environmental. Mr. Sittler has more than 30 years of technical experience in applied hydrogeology, with specialized experience in remedial strategy development and implementation. He has managed and performed hundreds of site investigations, audits, and assessments at industrial facilities, service stations, petroleum and chemical refineries, and landfills in more than 20 states, and has expertise in all aspects of remedial strategy development and remedial system design, installation, and operation. We also have with us today Mr. Barry Poling, Central Regional Manager here at Regenesis. He has 15 years of experience in the environmental industry, including extensive experience in Phase 1 and Phase 2 site assessment, remediation, and industrial compliance. He provides senior leadership in areas of site remediation, design, strategy, and business development. All right, that concludes our introduction. So now I'll hand things over to Steve to get us started.
Thanks very much, Dane. Hopefully everybody can hear me okay. If you have any issues with that, just please send a notification to Dane and we'll try to get that taken care of. But welcome everyone. Again, as Dane said, this is kind of a follow-up to a presentation that we did last year on the same basic approach, but there is some really valuable information that you will see here at the end of the webinar that we've collected and developed by analyzing that data and showing that not only does ERD work and that we've done it successfully, but how long it ought to take and when you might want to look at supplemental injection. So the presentation outline is going to go over first of all, just kind of a background on the process and some of the advantages of partnering with a good vendor technology partner like Regenesis and maintaining consistency across your sites. We'll have a little bit about our ERD design and application strategy, which we think we've done a pretty good job of putting together a plan that is successful when it's implemented over multiple sites. Then we'll discuss a few case histories and show some examples of the ERD successes that we've had at several sites. And then finally, a breakdown of our performance analysis of the 8 sites. You know, how long does it take? How much does it cost? Which is really what everyone wants to know all along. I think we've established pretty well that it works. And the question now is how long does it take and how much does it cost? Chlorinated solvents, as all of you know who work with them, have been around for coming up on 100 years now. They've been really heavily used since the 1940s. They're very persistent in the environment. They've always been known as recalcitrant compounds. Probably, and in my opinion, that's mostly because a lot of geologic environments are not anaerobic. And most aerobic environments, chlorinateds don't degrade very quickly, so they tend to hang around. They have really low default cleanup levels. In other words, they're very toxic. In fact, some of their daughter products, such as vinyl chloride, has a lower cleanup level than the parent product. So there's a lot of issues that chlorinated solvents have developed or have presented over the years that have been challenges to those of us in the industry that are trying to clean them up. A technology that's come into play recently, or at least recently in the terms of the environmental business the last 10 or 15 years, is enhanced reductive dechlorination. Basically, as this slide shows, that just involves an introduction of an electron donor, which is a substrate that's fermentable into the water-bearing zone, and also, and I believe this is very important, and we'll talk about this a little more, bacteria. There are many good reasons to add a bacterial culture or to do bioaugmentation and make the process go faster and and basically be a huge benefit to your project. And we'll go into why that is here in just a little bit. But this is just the basic process. When these compounds are added to the subsurface, the bacteria basically use the chlorinated compounds as part of their respiration process, and they remove the chlorines, and chlorinated compounds are degraded from the parent products of PCE or TCE, ultimately all the way to ethane or ethene, and that's really what we want to get to in the end. An important part of the process that we've developed is to end up selecting the right technology partner. There are a lot of different products out there, and some of them work better than others, some of them work better in different situations, but I've found that having someone who has a variety of technologies at their fingertips will provide me with support during the application and after the application, and has a lot of track record of success, like Regenesis has been very helpful to me. I've been working a long time with the folks there, and we've developed a partnership, and I think that's really important to have that relationship, so that you don't just get the product and move on, but you follow up, and that's really how this webinar came about, was the follow-up stuff that we did and the analysis that we did to show that the product worked. The last thing is to maintain a consistency through change. That's also very important. It's a process, it's a partnership, and being consistent all along and making the same decisions and using the same process across a wide variety of changing conditions and sites is very important. And I want to encourage everyone to keep that in mind the whole time, is that the way that we've been successful at these sites is not to just take one product and throw it at it, but to use the same process to determine what are the appropriate products, what are the doses we want, and where are those going to be. And that's a very important factor. This slide here is a conceptual site model, which is a key to success. It ought to go without saying that a conceptual site model that's properly designed and properly developed is key. Too often, I think people sometimes move forward with remedial designs or try to develop remedial designs of all kinds without really understanding their site. And if you don't have a good knowledge of the site conditions, the geology and hydrogeology, and where the impacts are located, and how much you might have in a soil that is going to act as a source, limitations that you may have in way of utilities and so forth, and even your remedial goals, that what are you trying to get to? If those things aren't well understood, then more than likely your design is not going to be a good one. And again, like I said, it should go without saying that you need to do that, but I think it's worth emphasizing, because failure to do that increases the likelihood of failure in your remedial plan, and there have been a lot of people who have done that. Another key in putting things together as part of your design is to have a lot of parameters that you know ahead of time. The more information you have up front, the easier it is to come up with a design that's going to work. If you've got minimal data, you don't understand the geology, you don't know your limitations, and you don't know your remedial goals, it's highly unlikely you're going to come up with a good design. So it makes it very difficult when you just say, hey, I got some contamination here, and you talk to the folks at Regenesis and say, let's take a look at it. If you have all this background information and you come up with kind of a plan yourself of, hey, this is where my contamination is, these are my issues, that just makes it that much more likely you're going to come up with a good design. So these are just some examples. This is a site evaluation form. That kind of information on the form may not be everything that you need. It's much more valuable to have other things, but it's a good start. And at a minimum, you need to have this kind of information to develop a successful design. Next thing I want to say about designs is that not only should they be site-specific, they should also be area-specific at a given site. These bullet items on the left are the factors that are taken into account when a design is put together, but if you notice on this site here, there are 3 different colors of blue over here on the right-hand side of the slide, and that is because we designed the injection specifically for 3 different portions of this impacted area. There's the the darker blue, which is the area where the spill actually happened. Then there's an area just upgrading of it inside the building where it kind of wicked in under the concrete of the building, and then the down gradient plume. And those had 3 different concentrations, 3 different injection amounts, and were specifically designed for this site. So randomly applying it and saying we're designing to the worst case would probably work, but it's going to be much more costly. And this is a good example of where not only are we designing for the specific site and the geology, we're designing for different parameters within the same plume. It's important to provide this level of detail. It just makes a huge difference. We've found, and you've probably heard from other folks before, that active monitoring of the biogeochemical conditions both before and after injection is very important. Collecting these data from your area that you're going to do the injection ahead of time can do 2 things. 1, it gives you a baseline to compare to later. Number 2, it gives you conditions that might help you tweak your design a little bit. If you based it just on the VOC concentrations, you may find there are other factors that would cause the design to be tweaked. All these parameters are valuable. I will say, just from my own experience, there have been very few sites in which there have been significant chlorinated degrader populations existing before the injection. Not going to say it doesn't happen, but it's not common. So that's an expensive analysis, and if you have a parent product and very little daughter product, you probably don't have chlorinated degraders, and that's something you might be able to overlook in the initial analysis. But the other parameters are important. They definitely should be analyzed post-injection to show that the populations have increased. And that monitoring period, the pre and post monitoring, is very important in making sure that not only that your injection worked, but identifying areas where you may have an issue that need to address later. There's a simple formula that's for success that we've found, and it's always good. I've been told to have an equation in every slide, so this is my equation right here. It's a simple addition equation. The donor plus DHC, which is Dehalococcoides or the bacteria, plus distribution equals success. We call that the 3 Ds. If you have those 3 Ds, you're likely to have success in an ERD project, and they're all equally important. The first D is the donor, which for all of these sites was 3D microemulsion. It's a product made by Regenesis that has an effective lifespan of 3 to 4 years at least. It's a 3-stage electron donor. It's very easy to handle and inject, which is why we selected it. It spreads out easily in the subsurface, does not require a lot of additional water, which is important in tight formations, and it's just much easier to handle than products that may be such as mineral oils or different kinds of molasses, those kinds of things that are just a little more difficult to handle.
All right, Steve, I've got a question here. In the slide, you mentioned an effective lifespan of 3 to 4 years for the 3D-ME. Is this consistent with what you've seen at your sites?
Yes, it's definitely true. We have a site, the first site we did, which has been almost 5 years ago now, but we discontinued monitoring about 4 years after the initial injection. And even in the area where we started, the first injection, which was actually a pilot study, that even at long after, years after the chlorinates had disappeared, it was still anaerobic. So there were still anaerobic conditions maintained. So the products are going to last a long time. The only reason you're going to see changes is if you have marked changes in the geology, a flooding event or a broken water line, which might flush things through it. But even then, we've had a couple sites where we had anaerobic conditions develop, and then there was a water line break, and aerobic conditions predominated, but then it went back to anaerobic afterwards. So it was temporary. So yeah, that's the 3 to 4 years is pretty consistent at most of our sites.
Okay, thanks.
The second part of the 3 Ds is the DHC, which is the bacterial consortium. In this case, it was Biodechlorination Plus or BDI Plus. We typically co-apply the 3D-ME with, or we co-apply the BDI Plus with the 3D-ME which increases degradation rates, and I'm going to have a couple slides here where we did a pilot study that shows why that's important. This is an electron microscope photograph of what the bacteria supposedly look like, but honestly I think they look more like this if you see them up close, because once they're given their food and their proper environment, they go crazy and they chomp those chlorinateds and they disappear rapidly, and you'll see that here in the next slide, or next several slides. The pilot study I mentioned, which is why it's important to apply Dehalococcoides at the beginning. This was a site up in northwest Indiana where there were two more or less side-by-side plots, and in one of the treatment areas there were 3DME only was added, which is slide or graph number 1 there at the top. In the second area, both 3DME and BDI plus were added at the same time, and then the results were monitored over time, period of about a year, as you can see on the slide. The thing that's interesting to note is that if you look at the blue line, which is the DHC populations, they ramped up at more or less the same rate, regardless of whether or not there are any bacteria added. But the functional genes, which are a measure of activity of the bacteria, did not ramp up quickly. In fact, it took almost 6 months before you started to see significant populations or significant amounts of these active functional genes. A good analogy to that is if you had a factory and you put 1,000 workers in it, but they didn't do anything, you're not turning out any products. But if you put 1,000 workers in it and they're functional and they're actually doing their jobs, then you can produce products. So again, what this comparison shows is that by putting the electron donor and the bioaugmentation in at the same time, you have a much more rapid buildup of the functional genes, and consequently the bacteria are working right away and more quickly. You can see by this next slide that the result is faster degradation rates. I mean, you don't even have to look at what the axes are in the graph. You can just look at the slope and see that the degradation is much faster and much more rapid when bioaugmentation was done at the beginning. In fact, up to 3 times as much more degradation in the first year. So, you know, if you feel there's a high likelihood that there's a good amount of bacteria there, and you know, cost is a really important issue, that might be a reason not to do it. But for the vast majority of our sites, we pretty strongly believe that bioaugmentation at the beginning is not only warranted, but it's a necessity to make things happen rapidly. And everybody wants things to clean up more quickly, and everybody wants to spend less money. And the amount of money you spend to put in the bioaugmentation is pretty small compared to the grand scheme of the product or the projects. And I think that makes it very worthwhile. The last D of the 3 Ds is distribution. The distribution should not be overlooked. It doesn't matter how well you've done the design and how well the products you select work if you don't get them where they need to be. You know, when you have daylighting or product coming back up the hole and spreading out under the asphalt or running out on top of the pavement, not only does that make people mad whose property is being treated, but it also doesn't do any good, because material running around on the ground is not where it needs to be. So it's very important to make sure that you have an experienced crew, you have the right pumps and injection materials available, and that you are flexible, because there's always going to be things that are different when you do an injection than what you expected. And you got to be able to adjust the mixtures and adjust the pressures, and that's what an experienced crew can do that understands what they're doing, is advise you on those sorts of things and make sure that the product gets where it's supposed to. Because in my experience, it's not a question of if it'll work. It will work. It just has to be gotten to the point where the contamination is.
All right, Steve, I've got another question. What techniques can you recommend for tighter formations?
Well, there are several things you can do. Number one, you can vary the pressure, the injection pressure, which is to to say you go one way or the other is hard. Sometimes you can put on high pressure and just hold the pressure and allow the material to flow into the formation gradually because it's tight. Other times it may be better to back off the pressure and try to almost gravity flow it into the formation. Second thing you can do is change the mixture. 3DME is very handy for that because it can be injected by itself if you have to. You don't have to mix water. It won't spread as far away from the point, but that's another option that we've used on occasion when the formation simply wouldn't accept the amount of water. It's also something to keep in mind during the design phase is that the calculations might say you need X amount of 3DME, which is recommended with X amount of water, and you may know that that's just going to be a difficult amount to get in there because of slug testing or wells bailing dry. So that's what you want to communicate to Regenesis when you're doing the design, is that that's an issue.
Okay, thanks.
Most of you probably seen this slide before. It's just a number of different ways that the materials can be injected into the ground. In my experience, we almost always do direct injection with the geoprobe. I have used some injection wells in a few cases, mostly when they were indoors and I didn't have enough room to have a geoprobe in there injecting, so we had to put in a shallow well with a hand unit and then inject into the well. The biggest negative of wells is that you better be right about the injection interval when you put it in, because you have the interval of the screen of the well, and that's it. The beauty of the direct injection is that you can move the rods up or down if you need to make the product go in a little more easily. So you have some limitations with wells, but sometimes because of the configuration of the site, or maybe on a site that's really deep where it's going to be expensive to do a lot of additional points and you know you're going to want to come back, you may want to consider re-injectable wells. But direct injection is probably 90% of the time has been my experience to be the best way to do it. Okay, we're going to talk a little bit about several case histories in which we used ERD successfully here in Indiana to remediate both TCE and PCE. This first site was a manufacturing facility in northern Indiana. There was an above-ground storage tank that did not have any, I guess, rapid leak. There had been drips and leaks over time. A TCE plume had developed. The original proposal was for an ISCO approach, in situ chemical oxidation. Thought that was kind of a difficult, costly approach for the site, so we proposed ERD, and this was about 5 years ago, and it was a little bit new to the regulatory agency. And so they asked us to do a pilot test and demonstrate that it would work. So what we did was a small pilot injection right in the source area. There was a well there, and then we monitored it for a few months. And this was the well that had the pilot injection. You can see there that the TCE had dropped down a little bit from the very first time that we had monitored it, probably because the plume was kind of moving off towards the north in a downgradient direction. The details of the injection are on the right there. It was a water table aquifer, sandy, 15-20 feet to water. The 13,000 square feet is a full-scale injection, not the pilot. The pilot was much smaller than that. But you can see on the yellow arrow when the ERD bioaugmentation happened, there was an almost immediate response in removal of TCE and production of cis-dichloroethylene, or CDCE. Vinyl chloride came just a little bit later, and it wasn't as much because it actually kind of knocked it down. And then there's a couple little blips out there in July 13 and March 14 as material dissolved out of the soil. But in the end, that one injection cleaned up that area. And after 6 months or so, seeing how quickly that happened, the IDEM said, hey, that looks like it's going to work at this site. Let's go forward with a full-scale injection. And this is an example of a well that about 8 months or 10 months after the pilot, we did the full scale, and you can see the same kind of behavior. Rapid production of daughter products. You actually had a little spike in the TCE concentration, which you'll see sometimes right after the injection because of pushing things around and so forth. But rapidly, within 6 months to 9 months, the TCE was removed and the well cleaned up, and basically that was the end of the story for that site. I also want to point out that lest anyone think we're just picking the best sites and the best wells, we're using these as examples, but all of the wells at all of the sites behave like this. There are some that required a supplemental injection, but we've got a lot of data that shows pretty much uniformly, as long as the material's gotten where it needs to be, you'll have this kind of 6 to 9 month period in which the parent products degrade. What we learned from it, or what we concluded from it, the pilot study showed that it would work, resulted in us not having to do pilot studies at some of our subsequent sites. We had dramatic reductions that continue with time. Within 3 years, with no supplemental injection, all the wells had achieved target cleanup levels, even some that were outside the injection area but downgrading of it. And we got a closure within in February 2016, which was a voluntary remediation plan closure 3.5 years after the injection. This is a certificate. That's what you want to get.
All right, Steve. Question here: was methane production a concern at this site or these sites in general?
Definitely not at this site, and in practice, not at any of the sites we've done. IDEM is concerned about methane production. It tends to be more of a problem when you have an in situ chemical reduction approach, an ISCR approach, than it does with ERD. Typically, the designs are based to encourage anaerobic degradation up through sulfonogenesis and to not push too far into the methanogenesis range. That's when I work with Regenesis to do those designs, we try to make sure that that's the case. So yes, we have seen methane production. Methane definitely does increase, but we typically have not seen levels in the wells that would even be above the regulatory agency screening level. And in the cases where we've been asked to monitor it, we haven't seen any gases in the wells above a fraction of a % of the LEL. So the short answer is no, methane production has not been a problem. The answer is, does it produce methane? Yes, you'll see a little bit, but nothing to be concerned about.
Okay, thanks.
The second case history we're going to talk about here today is a dry cleaner in southern Indiana. There were some vapor intrusion issues due to the residual impacts. There was a dual-phase extraction system with a remedial closure time frame of 7 to 10 years was proposed at a cost of up to $500,000 million, and that seemed to me to be both an excessive cost and excessive time frame. So we combined ERD with an ISCO injection directly below the floor of the dry cleaner to treat the materials in the backfill below the slab. The geology was a fairly tight clay with a sand lens at the bottom of it sitting on top of shale bedrock. So the water-bearing zone was a sand lens at the bottom of that. And so we basically treated the material directly below the slab with in situ chemical oxidation, and then we treated the material down in the water-bearing zone with ERD. We did see at this site, when we started, apparent degradation going on because there were apparent daughter products present. But as you'll see from this slide, when we did the ERD injection, this was one site where we did not put in bacteria to begin with, and we saw very little effect. The first 6 months where we had seen this at other sites, there wasn't a lot of degradation. I think it probably would have happened eventually, but we wanted it to happen faster. So 6 months after the initial injection, 8 months maybe actually to be exact, we came back and did bioaugmentation. As you can see from this slide, that's when we saw the rapid reduction in PCE and TCE.
Okay, thanks, Steve. Another question: isn't doing ISCO prior to ERD a little counterproductive?
Well, no, because it would be maybe if you did it right afterwards, but you need to allow time for that chemical oxidation to clear out and take place. In this case, the ISCO and the ERD happened in 2 different water-bearing zones or 2 different areas of contamination, so that was not a problem. But yes, if you were to do a chemical oxidation up front to try to reduce really high concentrations, you'd want to wait, a month or 2 to allow conditions to return to normal before you came in with ERD. So it is something to take into account, but they're not mutually exclusive and have to be used at different sites. So this site, it worked pretty well. We were able to reduce the vapors coming into the building from below the slab and also clean up the groundwater. As you can see from the green arrow, we did do a little supplemental injection to try to knock down some concentrations that were leaching out of the soil, and that's been pretty effective. In fact, I'll show you another slide from this site here. This was a secondary source area, which, because it's not directly below where the dry cleaning machine was, it was in an area where dry cleaning filters were stored. It cleaned up quickly and stayed that way. The site is currently anticipating closure. I said mid-2016. It's probably going to be a couple more quarterly monitoring events to finish up the end of this year. But we were able to shut down the VI mitigation systems. So those are done. All we have left is vinyl chloride that is is left above the vapor intrusion or groundwater migration to vapor intrusion level. So really all we need to do is allow that vinyl chloride to continue to degrade and we'll be done. Saved a bunch of money over the proposed system, and the lesson we learned was it makes good sense to put the BDI plus in right away because that just makes things happen faster, and we probably cost ourselves a couple of monitoring events by not doing that. The third case history I'm going to talk about here is a manufacturing facility in eastern Indiana. There was a guaranteed project budget, in other words, a guaranteed closure with a fixed budget. A dual-phase extraction system was originally designed and installed at the site, and it actually did a good job, except it was about a $350,000 system, and it removed everything it was going to remove in about 6 months. So it did the job, but it did it so quickly that it was almost like, wow, that's a lot of money we spent to get that fairly small benefit. There was an additional source area that was identified. When that happened, the decision was, do we expand our system and continue to run it, or do we do something else? What we decided to do was to do ERD in the new source area and then also do an ISCO injection in the hot spot. So Barry, this is kind of a good example where we were doing 2 things at the same site in 2 different areas. And what we found when we did the ISCO injection was successful in knocking the concentrations down. What we found from the ERD was that when we had concentrations up in the 3,500 part per billion range of TCE, and when we put the material in the ground, it just wiped it out in 6 months. And rapid production of DCE and some vinyl chloride, a little bit of TCE, but the well that was in the center of this area that had been the source of the issues was quickly degraded, and it's told us that, well, before I say that, let me move on. Let me add that here's another well that showed the same thing with even higher concentrations, 9,000 parts per billion. It worked very well, and it made us think that we might want to apply that across the whole plume, including in the area where we had done the ISCO injection. So we did that. We came up with a design that shows, you can see some of the remedial system on the site here. You can see the orange is the injection areas. The new injection area that we did first was actually up in the green box that you can just see a little bit of in the top central portion there. But we employed this across the site, ERD in these areas, to treat the residual impacts, including, as I said, right here in the center around well 8. That was where the ISCO injection occurred. So this is a perfect example where we followed ISCO with ERD in the same area and saw a successful result. Here is well 8, which was that hot spot core. You could see when the ISCO injection happened, it was successful. It did knock concentrations down, but we were still dealing with, trichloroethylene concentrations in the 1 to 2,000 part per billion range, which is far too high for us to get closure. So when we came back with the ERD injection, again, same thing we've seen across the board. Rapid production of daughter products, elimination of the parent products. Daughter products, you can't really see it on this scale because the numbers are too small, but there were some hits between 0 and 1,000 for the daughter products that just aren't visible to scale. But those were minimal, and at this point, I think it's been 6 quarters in a row we've had non-detect in this well. So we're pretty much done. The new source area ERD injection wiped out that issue. The core area knocked it down within 24 months, and really before that, that was on the far end of it. There was a small supplemental offsite injection earlier this year, which was designed to avoid having to do mitigation at an offsite property, and that worked as well. Concentrations are down to nothing, and in a couple more quarters, the site's going to be eligible for closure. So that was another success story that kind of shows you that you can apply different kinds of solutions at the same site equally effectively. All right, we've shown you that through these case histories that ERD works, and you probably saw, if you looked at the shapes of the graphs, how quickly it works. But what we're going to show you next is a performance review of 8 sites that tells us exactly how quickly it works and how we can use that information to better improve supplemental injections and to interpret the data that we get. So just quickly, there's 8 sites in this group. And you can read the slide yourself. 4 industrial, 4 dry cleaners. There's a total of 36 wells that we reviewed. All of the injections we did at these sites were grids. They weren't lines or barriers. You can see the average concentrations. Some of the sites were nice sandy areas. Some were clay with sand lenses. Of course, in all areas, we focused on injecting into the permeable portions of the formation. And we were trying to achieve risk-based closure goals, not get it to non-detect in most cases, although in some cases we did anyway. And then this is just another little bit more information about the sites. The size of the injections varied from as small as 1,000 square feet to more than 66,000. 3DME injected similarly was a wide range of gallon volumes, and BDI plus as well. Most of these sites, about 30% of them needed a supplemental injection, which typically runs in the neighborhood of, well, let me say that again. About 60% of the sites needed supplemental injections, which average about 30% of the volume of the initial injection. So more than half the time, you're probably going to have some supplemental injection needed. It's just going to be a little, it's going to be substantially less. This is probably the critical slide of the whole presentation of how long ERD takes. This is a summary of all the data we crunched, and what you're looking at here is the dark bars on top of each compound is the number of days after the application where the peak concentration was detected. The medium bars are when we achieve 75% reduction, and the lighter bars are when 90% the reduction was achieved, which was kind of, we actually achieved more than 90% at most sites, but that was more or less in our target goal for most of the areas, which is why we used that. But I'm going to look at these individual compounds a little more closely here in the next slide. For PCEs, you can see it peaked about 19 days after average, which means we sometimes saw numbers going up right immediately, but within about 180 days, we had 75% reduction, and within 260 days, we had 90% reduction. So PCE was eliminated at about 240 days, or 6 months, or excuse me, 9 months or so from the time that the peak concentration occurred. Pay attention to the second bullet on each of the next of these slides, and because you're going to see something kind of remarkable about how consistent the time frame was that the different compounds degraded from peak. So in general, 180 to 260 days of PCE is gone. TCE is pretty similar, slightly longer. In some of the cases, TCE was the parent product. Other cases, it was something that was produced. So that's why you see a little bit longer peak concentration and a little bit longer time to eliminate it. But if you look, the days after the peak to be 90% reduced is almost the same as PCE, 160 to 240, 160 to 210. So you have a very similar time to concentration reduction for TCE after peak. Cis-DCE typically is eliminated 330 to 370 days on average. Again, the days after peak is about the same, so you're looking at a year until you're down to just vinyl chloride, and then vinyl chloride around 400 to 405 days, or in the ballpark of a year and a quarter to a year and a half. So once you get to this point, you're done. Again, notice that 170 to 200 days after peak is about how long it took for the vinyl chloride to degrade. Pretty much 6 months. That's what this first bullet says on this slide. It's strikingly consistent degradation of the different compounds once they hit their peak levels. The other thing there are two other things to notice. Number one, you can use these data to determine when you have a problem wells or dogs, as we like to call them. You look at the PCE time frame and you see that we're not getting PCE complete reduction or TCE if that's apparent within 260 to 280 days. You probably have an issue, and that might be a well you'd want to consider a supplemental injection. So once you've spotted those dogs, it's good to go after them, because as someone once said, hope is not a strategy. And sitting there hoping that it's going to degrade when you know from data like this that it's not going to it's a pipe dream. You're not going to see it. Go after those wells that need help. A couple quick slides here on cost. In general, we found that ERD costs about $7 to $15 per cubic yard of plume treated. That's calculated by taking the footprint of the plume times the injection interval. That's much cheaper than chemical oxidation, which is more appropriate for smaller, very highly contaminated areas, and way higher than mechanical systems due to capital cost and the investments you have to make in a system up front. There's typically 6 figures for a remediation trailer and the piping and stuff before you even remove anything. So it's a very cost-effective option. Our costs have ranged from around $40,000 to $300,000 for materials and injection. That's just my cost. That doesn't mean that smaller amounts or larger amounts wouldn't be an appropriate and cost-effective approach. It's just what I've seen. $300,000 is a lot. You can treat a pretty large area with that much material. This was a hypothetical example that we did, which is kind of a generic site based on the average of what we've seen. And if you look at this, you can see that ERD is significantly less expensive than other options that are commonly used, such as pump and treat or air sparge, which are mechanical systems, or ISCO. Now, is this going to be the case at every site? No. That's why you do the site investigation, develop a conceptual site model, and select the most appropriate approach. But frequently, ERD is going to be more inexpensive than most mechanical options at most sites. So that's just been my experience, and I found that to be the case. What did we learn here today? What are the lessons? Well, I can't say it enough. A well-defined conceptual site model is critical. If you have good data from the conceptual site model going in, you'll develop a good design, and that'll help you do a good application, and then you'll end up with a successful result, and everyone will be happy. It's always beneficial to do bioaugmentation early. I think we saw that ERD happens quickly. We got full reduction within a year and a half at most of these sites, and reduction of the parent products within 6 to 7 months. And we learned to be aggressive with our supplemental injections. If you need to, get in there and do the supplemental injection, keep the process going, don't monitor and hope that it'll clean up if the data don't support it. So remember the 3 Ds. If you do those 3 and you have a good conceptual site model, your design will probably be successful, and you'll see results like we've seen at these sites. So that's pretty much all I have today. I'll turn it over to Barry, and we'll see if there's any questions that any of you may have had throughout the process.
All right, great. Thanks, Steve. For the first question, you suggested that DHC or BDI plus be applied concurrently with the 3D mean. What do you mean by concurrently?
By concurrently, I mean that we do the injections at the same, not in the same hole, but at the same time. We like to do the 3D-ME first and get all that in the ground, and then come back immediately and put in the BDI plus. Bacteria are very oxygen sensitive, so it's important to use deoxygenated water, or water that's been sparged of its oxygen with nitrogen before you do that injection. But typically, we don't think we have to wait, 6 months or 3 months or a month or anything. We typically do all the 3D-ME first, come back and do all the BDI. If it's a long injection, you might do 2 or 3 weeks between the time that you finish the 3D-ME injection and come back with the BDI. But by concurrently, I mean do it in the same, mobilization, the same injection phase, and don't wait. There's no reason to wait, but we do them separately.
Okay. And to extend upon that, do you always recommend adding DHC, or do you evaluate it before recommending it or applying it?
I mean, in my experience, there's been very little DHC at most sites where we've done a pre-evaluation. And again, as I said, those analyses are kind of expensive. They're about $350 a pop. So, if you do 6 or 8 wells, you're looking at several $1,000s, and most of the time you end up having little to no bacteria. So if there's a compelling reason that you think there might be bacteria because of the presence of daughter products, or maybe the presence of a plume of hydrocarbons that is commingling with your chlorinated plume and causing a reductive environment, then it might be worthwhile. But I think for the most part, adding bacteria up front is going to be your best bet, and unless you have strong reasons that that's not the case. Again, the cost to do it typically is not much compared to waiting and doing it later. And if you know from the data that we've shown you that adding the bacteria to begin with is going to be a positive step. So I look at it as a rather inexpensive add-on in the grand scheme of things that has a huge benefit.
Okay. All right, so another question. Are the injection times temperature, weather, or seasonally dependent?
In theory, no. In practice, yes. I mean, the ground doesn't change much. The temperature of the ground doesn't. So from the perspective of the materials going in the ground and the bacteria, it's going to be 55 degrees in the ground. It's not going to make too much difference, but it's a huge pain to have to try to inject fluids in freezing temperatures. We here in Indiana have freezing temperatures for several months a year, and that's why I say in theory, no, it doesn't make a difference to the bacteria themselves, but it's tough to keep the materials. The materials themselves don't freeze as much as you have problems with water, your joints and your pipe connections and all the things in your geoprobe. So we have done a couple sites where we built little shelters around the drums or the totes of 3D-ME and kept them warm, and we're able to do that. But even at nighttime, you have things freeze up, and if you're going to do that, you probably better have some leeway built into your budget to deal with the issues of cold, because it's not so much the products, it's just the mechanics of doing it. It's just tough, and guys don't like it. They have to go out and do it either.
Okay, and then beyond that, and I know we've talked about this, rain events. I know rain has affected some of the geochemistry at some of your sites.
Yeah, you have to keep that into account when you're timing your injection. If you're in an area that gets a lot of seasonal rain, you might want to think about maybe not doing it in the spring, when, especially in a water table condition. We had one site where the water table was only about 8 feet deep, and it was sand, and we injected and we got some positive results, but not as good as we would have liked, because they happened to have, in the 6 months or in the 3 months after we injected, they had about 13 inches of rain, which is way more than normal, and we believe that counteracted our attempt to create anaerobic conditions and flushed a bunch of oxygenated water through the formation. So if the water is deep and if it's not a water table situation, if you've got a sand lens or stringer, then I think perhaps that might end up being not being as much of a concern as it does in a water table, especially a shallow water table. But yes, certainly something to think about.
Okay, great. So what is the scale or size of plumes that you're treating?
Well, that's, as we talked about, some of the the square footage there. They've ranged from as small as 1,000 square foot to as large as 66,000 square feet. We've actually got a couple sites that we're working on right now that have larger footprints than that, up to 150,000 square feet, maybe even 180,000 square feet. So it works in a large variety of situations. The bigger the plume, the more you have to rely on transport of the materials by injecting them in barriers or lines. That increases the time it takes to clean it up. Obviously, if you try to do a grid across a plume that's a quarter-mile long, it's going to be ridiculously expensive. So barriers work well. They just take time to operate. One of the sites I did barriers on took about a year for the material to move down gradient to a well that was maybe 70 or 80 feet away. That's about what we expected, but we had to do that additional monitoring during that period, and the well basically looked like it wasn't cleaning up. But as soon as the material got there, it did.
Okay. So what factors determine whether to use ISCO or ERD?
Well, that's, in my opinion, in my experience, that is typically, there are two things. One is concentration. We have effectively used ERD on some really high concentrations, up to 70,000 parts per billion of a parent product. But it's probably more, if you can do chemical oxidation and knock those down, it will make it easier for your ERD injection to follow on. You may not need as many supplemental injections or as big of a supplemental injection. ISCO is a contact-based approach, so the materials actually have to physically contact all the contaminants. That has to be taken into account. That's a permeability issue. Whereas the bacteria will tend to move around a little bit as the water moves. They'll some adhere to soil, but some will flow, and so you don't have to worry about them actually contacting. They will, I don't want to say they'll seek out, because they're not like little hunters going around hunting for the chlorinateds, but they're looking for food, and as the food comes to them and as they migrate, they'll use it. So kind of a combination of concentration and ability to get the material into the ground and allow it to move around.
Okay. And this is an extension of that last question, and you partially answered it already. At what high-end concentrations have you seen ERD effective, and is it effective on free product or DNAPL?
The DNAPL question is easy. The answer is no. It doesn't directly affect DNAPL. DNAPL will act as a continued source. If there's DNAPL present, even if it's just globules or droplets that don't show up in the well, that can often be an explanation as to why a well isn't cleaning up as quickly as you'd like. So it's not effective on free product, but it is effective on very high concentrations. I've used it on concentrations as high as 70,000 parts per billion. In fact, the higher the concentration, the more rapid you'll see degradation. So you can see success quicker in the higher concentrations, because it's a lot easier to knock something from 10,000 to 500 than it is from 50 to 5. That's just how, it's like losing weight. It's a lot easier to lose that first 20 than the last 20. So same thing works with these. It's much easier to knock down the high concentrations. And I haven't seen a concentration that I would think was too high, but if I saw anything up over 100, I would strongly suspect there was some DNAPL there, even if it wasn't showing up in wells, and to be wary of that and maybe try to address that some other way before I came through with ERD.
Okay, great. Going back to your cost comparison at the end, did that cost include or the ERD cost include BDI and 3DME?
Yes, so that cost range included the products, both 3DME and BDI, because we used them in all of our sites. It also included the drilling portion of it, the geoprobe and the injection pumps and the materials, and it included the labor time for the crew that was out there doing the injection as well as project management. So I kind of rolled everything together. That's, that was our project budgets, soup to nuts, materials, injection, management, oversight. There wasn't anything left out that other than obviously the assessment cost to determine what the problem was not part of it, nor was any post-injection monitoring. Typically our monitoring periods are in Indiana 8 quarters is kind of a standard, although we've gotten away with less than that. 4 quarters following some supplemental injections because of it was obvious that it was degrading. It was just a matter of demonstrating that the add-on finished it off. Typically when you have to do longer injections, if you get any spikes in your data, and you have to go back and do some of those things down the road.
Okay, so I've got a pH question here. If your pHs are low, generally around 5.5 at multiple locations at the site, would you still try this ERD?
That's pretty low. I would probably be reluctant to do that unless I could buffer the pH ahead of time somehow. The worst thing with low pH is the degradation of daughter products. We've seen some decent degradation at 6 or a little below 6 of PC and TCE, but when you get to cis and vinyl chloride, they are very sensitive to pH. So when you're talking 5.5, that's pretty low. I would want to try to do something to buffer that before I would think of ERD as a good solution. And I don't see that very often, but in cases where we've had issues with that.
Yeah, and I'll add to that. I think partially in the areas that we work here in the Midwest, where most of these examples were presented, we deal with naturally buffered aquifers. So, what I see from the Regenesis standpoint is that it is regional. And, southeast, for instance, we see a lot of low pH aquifers down there, which presents a challenge for ERD.
Yeah, I would agree. Anytime we have that, which is not as common here, it often develops after the fact. That's a challenge.
All right, so just a few more, maybe one more. Do you have any experience with injection in horizontal wells?
None of the sites in this particular portfolio used horizontal wells. However, I know that Regenesis has done horizontal injections at a number of sites, and it certainly would work. I didn't use them at any of these sites because I didn't need to, but that would be a good application under a building or under a street where you couldn't get at it, angles. That would work well.
Yeah. Now
you
I'll
might be
add
able
to
to
that.
add on that with some of your experience.
Yeah, so to answer that question, yes, we do have experience. Regenesis products have been injected via horizontal wells. Okay, so one last question I saw jump up here, which we can clarify pretty quickly. I thought you mentioned an application for vadosone. Is that correct?
We typically don't inject in the vadosone just because, again, the fluid's not going to move around much in the vadosone. It's not under any gradient like groundwater. We do frequently inject above the top of the water bearing or top of where the water is, especially in water table aquifers because of the fluctuation. We want to get some material up there for when the water moves up and down. But to use it as a vadosone treatment, I don't think that would be a good approach. I would say the same thing about ISCO. I mean, you'd have to fill every pore space with fluid, and you know that's not going to happen because it's going to take the path of least resistance. So vadosone treatment is better off using some kind of like SVE, a mechanical removal. Fluids are not good for that, introducing fluids to vadosone.
Okay, so we are at the top of the hour here, and so Steve, I appreciate your time and doing the presentation, and that should be it for us. You can see our contact information up here. I also want to acknowledge Doug Davis, who's also our partner in this, and he was very important in putting together doing this work and putting together the performance review.